If you recall, we've been in the middle of spending way too much time on trigonometric substitution. And last week we left off with the trigonometric substitution. We're in part 2, the integration phase. Remember the 3 phases of trigonometric substitution. The first is to substitute your x integral into a theta integral using one of the 3 cases. We have some kind of quadratic form in our x integral, and we can take 2 terms and make them 1 term through a trigonometric substitution and a Pythagorean identity. That was the whole point. If you're not using a Pythagorean identity in your trigonometric substitution, then there's no reason for you to be doing your trigonometric substitution. The resulting theta integral will either be even powers of cosine or odd powers of secant. Specifically, the cases where we're not able to do substitution on the theta integral. If we can do a substitution on the theta integral, we should go back and do the substitution on the x integral because there will be one there. So specifically, we want even powers of cosine without odd powers of sine, or odd powers of secant without even powers of tangent. So these are the 2 cases where we don't have a convenient substitution to make. In both cases, we can use parts. In the case of cosine, we can use parts, but we're not going to want to use parts. We're going to want to use a double angle identity. So last week, we talked about the odd powers of secant case, and we had to have one that wasn't parts. The integral of secant theta to theta is the natural log of the absolute value of secant theta plus tangent theta plus c, obviously. That's what everybody had guessed. But then we went through the process of actually finding this, and the trick was to multiply by 1, but 1 in this special form, secant theta plus tangent theta over secant theta plus tangent theta. That allows us to do substitution, and you can see what the substitution is. W was secant theta plus tangent theta, and then so dW was secant theta tangent theta plus secant squared theta. That was nice and straightforward. It is not critical that you remember how the integral of secant theta is equal to natural log of absolute value of secant theta plus tangent theta. You just need to remember the end result. All right. So for odd powers of secants with even powers of tangents, we're going to use parts. So specifically, if we have secant cubed theta to theta, our strategy was to use parts. We had to choose dV as something that we could integrate. And the one that worked out for us was set dV to be secant squared, and then keep u as just one of the secants. So we've decided on our two given parts. So we differentiate to find du. So derivative of secant theta is secant theta tangent theta. And d theta. And the integral of secant squared is just tangent. We tried various combinations of what we can put in for dV. And this one gave us the best secondary integral. Now that we've got our 4 parts, we put together in the parts formula. So we're going to have uv, or secant theta tangent theta, minus the integral of v times du. So I have secant theta tangent theta times tangent theta. So that's going to give us a tangent squared theta. So we'll have secant theta tangent theta d theta times another tangent of theta, which will give us a tangent squared theta. Now our secondary integral is still 3 powers of things. So in that sense, it didn't get any better, but it also didn't get any worse. We had to start off with 3 powers. We've got 3 powers. The idea is that we could separate out this tangent squared theta. So we're going to break this tangent squared theta. We're going to write that as secant squared plus 1. Secant squared minus 1. Which one is it? Is it minus? All right, thanks. I should remember that because the secant case is x squared minus a squared. So that tells me I want secant squared minus a squared. So that's how we can remember our Pythagorean identities. Now we can distribute the secant, and our secondary integral will be a secant cubed minus secant. So I have, this is going to be the secant theta, tangent theta, minus the integral of, when we use the distributive property, secant cubed distribute the negative, becomes plus the integral of secant theta. So we're going to separate out the 2 terms. This seems weird because trigonometric substitution is all about taking 2 terms and combining them into 1 term. That's in the substitution phase. Now we're in the make shit up as we go and try to integrate the function in front of us phase. And to do that, we're going to break up the secant cube and a secant. Remember what we started with was 3 powers of trig functions, and we ended up with 3 powers of trig functions, but we were able to set it up to separate to 3 powers of trig function here and only 1 here. Here is where our reduction happened. It doesn't matter that we didn't reduce the secant cube because that's what we're trying to find. What we're going to do is we're going to add what we're trying to find to both sides of the equation. Oops. So I'm going to add 1 term of secant cubed theta d theta because this is what we're trying to find. So over on the left, through our shenanigans, we have come up with 2 of the thing that we're looking for. 2 integrals of secant cubed theta d theta is secant theta tangent theta. This term has been moved, and the integral of secant theta, which is natural log of absolute value of secant theta plus tangent theta plus some constant. This is one of the fun things that we get to do with parts sometimes. Our original integral shows up as one of the terms of our secondary integral. And so the strategy is to move all that stuff over. And then up to get the one that we're looking for, integral of secant cubed, we just have to divide by 2. Remember that C is an arbitrary constant, so C divided by 2 is just some other arbitrary constant. If you're uncomfortable with that, call this C1. Then when you divide C1 by 2, you just get C. If you want to be a little more specific with your arbitrary constants. Yes. So this term of secant cubed is negative because I have a negative secant times secant squared. That's the secant cubed. This was positive because I have a negative secant theta times a -1, so that cancels out to positive. And this line here is us adding this term to both sides. So then it cancels out here and then shows up over here as a 2. So notice that during this part, we learned one of our cool parts tricks where the original integral shows up in the secondary. Add it to both sides, you'll just get a constant multiple. This is one of parts' one of the cool party tricks for parts. Also note that we could not do substitution on this integral, so we switched to parts. That is a very standard thing to do. Substitution not available, try parts. Parts not available, do something else. In this case, parts work. The other thing that was in play here is us just remembering that the integral of secant was natural log of absolute value of secant theta plus tangent theta. Let's look at the next one and see how these same things come into play. So the next odd power that we care about is secant to the 5th, and we're going to do the same thing what we did before. And the same elements are going to happen. Our secondary integral is going to have a secant to the 5th in it, and it's going to rely on, and the other 2 terms that show up out of that are going to be a secant cubed and a secant. I might actually skip that, so only the secant cubed will show up. But if the secant cubed show up, that means the secant showed up, if we remember where things came from. We know that this is not substitution because it's an odd power of secant without tangent. So we're going to set up a u and a dv. dv has to be something that we can integrate. Now, although we can integrate secant cubed, we do not want to use that mess in our secondary. We want something simple. We're going to do the same parts that we did for secant cubed. dv will be secant squared theta to theta. And that leaves u to be secant cubed. We're deciding on parts. dv has to be something we can integrate. Worked out great last time when we just integrated secant squared. Let's try that. We take the derivative of u to find du. The derivative of u is going to be 3 secant squared theta times the derivative of secant theta, which is secant theta tangent theta. Which we are going to simplify to 3 secant cubed theta tangent theta, d theta. And at this point, we should recognize that we are in the same situation that we were in the previous one with secant cubed. There's just more of it. Our dv is going to be tell us that v should be tangent theta. That tangent theta is going to bump our tangent theta from the du up to a square. We're going to replace the tangent squared with secant squared minus 1. And we'll be back to where we were in the previous problem. So our integral is going to have, our uv is going to be secant cubed theta times tangent theta minus the integral, pull 3 out, of secant cubed tangent squared. This is the same thing what happened in our secant cube. We started off with 3. Our secondary had 3. Here we started off with 5. Our secondary has 5. And we're going to get out of it in the exact same way. We're going to replace tangent squared with secant squared minus 1. And we're going to distribute this. One of the integrals that's going to show up from our secondary will be a secant to the 5th, which is the one that we're looking for. So we'll put it aside. The other one is going to be secant cubed. So I've still got the secant cubed theta, tangent theta. I'm going to have minus 3 secant to the 5th. Then minus and minus will become plus, and there's still the 3 secant cubed theta. So even though we ended up with 5 factors, after starting with 5 factors, we can break our 5 factors into 5 factors into 3 factors, and we know the 3 factors. The 5 factors is what we're looking for, and we know the 3 factors. So we're going to do the same thing that we did before. So the secant to the 5th, the integral of secant to the 5th theta is what we're looking for. So we add that to both sides. We just gather all those up, all those like terms. And the remaining second part of the secondary integral to secant cubed is one that we already know. So this is just us knowing the integral of secant cubed is a 1/2 secant theta tangent theta plus a 1/2 natural log absolute value of secant theta plus tangent theta plus c. That's not me actually remembering that. I'm looking at it right here. This is why I do 3rd before 5th. Now we just need to divide by 4 and maybe distribute the 3 to make it look really excessive. So our secant to the 5th, our integral of secant to the 5th theta to theta is going to be a 1/4 secant cubed tangent plus 3/2 divided by 4, so 3/8 secant theta tangent theta plus 3/2 divided by 4, 3/8 times the natural log of the absolute value of secant theta plus tangent theta plus c. At this point, we have enough information to suspect that there's probably some kind of pattern. Integral of secant was just one of these natural logs of this sum. Integral of secant cubed had a secant tangent plus the natural log of the secant plus tangent. The integral of secant to the fifth had a secant cubed tangent, a secant tangent, and then the secant with no tangents. So we suspect that the secant to the seventh will have some kind of secant to the fifth tangent, a secant cubed tangent, a secant tangent, and then this natural log of secant theta plus tangent theta. Only thing we have to sort out is what the coefficients would be, because the coefficients seem to be doing some stuff. You also may be wondering, hasn't someone worked this out before? And the answer is yeah, totally. We have worked out a lot of these. I say we, like I was there. But Wolfram Alpha has them all worked out as well, and that is the point. Any questions? Kind of like the Chat GPT thing. Educators are worried about Chat GPT because students are going to use Chat GPT to write their entire essays. And right now, the weak ass argument against that is like, oh yes, but it's super obvious that an AI has written your paper. Like, well, right now it's super obvious. It won't always be super obvious. Especially if you go into a field that promotes having a definitive style in your writing. Like you're supposed to write things a certain way. I watch people worry, oh no, what's going to happen? How will we catch these students? And I'm like, oh, that's very American of you. How will you lie in wait and catch people? Like all the math teachers in the world are like, oh, dude, we've been dealing with this ever since like the internet. And people just looking shit up for our math problems. Because there really is. There's no plagiarism here. This is just like how this is done, right? So at this point, you could probably tell, I am not going to ask you to replicate the integral of secant to the fifth. That would be ridiculous. All you have to do is write this. And even if I don't give you a page of notes where you just like copy it down, then you just memorize it. And then the test is not about whether you understand how integration works. The test is just whether how good you are at memorizing shit. Does that make sense? I guess what I'm saying is I'm opposed to the culture of trying to catch students, because that makes me have to act like a cop. And I don't want to act like a cop. I don't want to sit there hidden on the highway waiting for someone to speed by so I can catch them doing something wrong. I'd rather set up a system whereby, you know, people don't fucking speed because they have respect for their fellow human beings. And in response to that, I would set speed limits up to something more reasonable and in line with modern auto living. 30, it's 80. My choice would be 80 miles per hour. But if I set a speed limit at 80 miles per hour, it's 80 miles per hour plus a tolerance on your speedometer. Anything over that, then I have to stop you from driving, because now you're making things unsafe. Do it once, you get a ticket. Do it twice, you're building a habit. So you do it once, you get the ticket. Do it twice, you just don't get to drive anymore. Now, that might seem like a harsh penalty, but also in line with what I want to do is there'll be public transportation. So not everybody has to have a fucking car. Because we can't consume our way out of a problem that we consumed our way into. See how it works? Everything is connected. And you can't just fix one problem. And you also can't solve problems by encouraging people to participate in the problem behavior. We all know why the police are going to sit there in line wait so they can catch you. Gotcha. That's like the whole gotcha mentality. It's so fucking stupid. They lie in wait so they can catch you because that's how cities and counties create revenue. So I'm like, okay, you're going to lose a revenue stream when I stop having you write all these bullshit tickets, because we all know that driving 70 miles per hour is technically over the speed limit, and technically you can get a ticket for it, but no one fucking does unless the city needs more money today. If your rules ain't rules, then your rules are bullshit. But anyway, keep following the problem until you can start fixing all these things. What does that have to do with ChatGPT? We live in a world where AI can generate language. And smart students who want to be efficient will use the AI to generate language and then make it not sound like so much like a machine. Go and give it your own voice, fix all the wonky things. It's the same way as if you're using Wolfram Alpha or a TI-89 to do your math problems. You use Wolfram Alpha to generate your answers. Then you look at that and say, oh, that's not going to look right. That looks machine generated. Leach is going to recognize that because I'm familiar with how Wolfram Alpha displays things. And I'm going to recognize it. I can 100% tell when you just copied your answers off of Wolfram Alpha, because it writes things in a very strange way sometimes. With certain things, no. With polynomials, that's going to be fine. Can't see that. But if you're using Wolfram Alpha to integrate polynomials, what the fuck, man? It's so easy. Why would you do that? You're spending more effort cheating than you are just doing the work. So anyway, instead of setting up a system where I have to be on guard to try to catch you from doing wrong, I want to set up a system where I encourage you to not have to do that. I want to set up a system where we remove the reason for lack of a better word, the crime. You know what I mean? Poverty. It's poverty. You need to get rid of poverty. That will fix a whole shit ton of things. So anyway, I'm worried about this because I'm listening to a lot of stuff about ChatGPT and some dude, I can't remember his name. I'm sorry, dude, who wrote this, but wrote some code that can try to distinguish between human speech or human writing and AI writing and kind of identify. Uses the way that humans write things and it essentially compares the two. And he specifically said, I don't want this to be used as like a catch-pole for teachers. And I'm sure teachers are like, oh, I want to use this to catch my students. Like, oh, why do your students feel the need to cheat on your shit? Maybe that's the problem that we need to address. You know what I mean? Anyway. Let's integrate secant to the 7th. I'm just kidding. That's ridiculous. I really don't want to do that. But if you're interested, take a look at what happened to these. Try to speculate on what these terms will be. Try to speculate. You know what the terms are going to be. Try to speculate on what the coefficients will be. Where'd that 4 come from? That 4 came from the 3. Where'd that 3 come from? That 3 came from the derivative of secant cubed. So if I up that to a secant to the 5th, what's that 3 going to become? That's going to be a 5. I'm going to add it to both sides. It's going to be a 6 over here. I'm going to expect a 6 to show up in my denominators. Because you know you're going to have a fifth secant to the fifth tangent, a secant to the third tangent, a secant tangent, and then this term. We just need to figure out what those coefficients are going. And with your secant to the seventh, you're going to have a bunch of secant to the sevenths. Well, it's going to be 5. We know where that comes from. 5 secant to the sevenths, and there's going to be 5 secant to the fifths. So it's going to be 5 of these. Anyway. If you hit the end of the day and you haven't done enough intellectual exercise, and you want a little bit like going for a run for your mind, just going jogging for your mind, integrate secant to the seventh using parts. Look for these things. I'm not going to assign it as a problem because it's like going jogging, right? But sometimes it's nice to go jogging and just shut your brain off and do jogging. Sometimes it's nice to grab some wacky integral and just go jogging and shut your brain off. Good intellectual exercise. So we have now solved, we have now solved the integrating odd powers of secants. The next one we need to deal with is even powers of cosine without odd powers of sine. If there's odd powers of sine, it's just a substitution problem. If it's even powers of cosine and even powers of sine, that's just even powers of cosine. That's how we're going to phrase that. Since it's already come up with the tangent thing, it's specifically even powers of cosine without odd powers of sine, or even powers of cosine paired with an even power of sine. Essentially, non-substitution. The reason we need the odd power of sine to make the substitution, or the odd power of cosine to make the substitution, is I need one to be the dw. That's why it's different than our secant case, because our secant, the derivative of secant is secant tangent, 2, second degree. The derivative of tangent is secant squared, 2, second degree. But the derivative of sine is cosine, first degree. The derivative of cosine is negative sine, first degree. So that's why we care about even powers of cosine and odd powers of secant. In the case of cosine squared, sine squared, although we could do the double angle identity business with the sine squared, usually what we're going to do is turn it into things that we already know. Replace the sine squared with 1 minus cosine squared. And then just distribute. So this will be the cosine squared minus a cosine to the 4th. We are usually just going to be phrasing things in terms of cosine. We had to pick one. I'm sure there's some alternate universe out there where they talk about even powers of sine without cosine. I've been there, it's nice. So we just worry about even powers of cosine. Now we know that these aren't substitution problems. That's why we're going over these in such horrifying and exhaustive detail. We know it's not substitution. Our next strategy is to use parts, and parts is perfectly viable for this, although a little bit excessive, especially if we've got higher power. So to see cosine squared done by parts, you can check example 6 and 7.2. So this is an example done in example 6 of 7.2 using parts to integrate cosine squared. It does involve this cosine squared showing up in your secondary and then gathering it. Well, let's just call the trig identity which one it is. So we are going to use a double angle identity. We're going to replace a cosine squared with a half plus a half cosine of 2 theta. This is not the base model of the double angle identity. The base model of the double angle identity we're using is cosine squared minus sine squared equals 1. Cosine squared minus sine squared equals cosine of 2 theta. So the base model double angle identity in play here. And that's not even the base identity we're using for this. The base identity we're using for this is the cosine of a sum. Cosine of A plus B is cosine A cosine B minus sine A sine B. Remembering all your trig identities is really hard if you try to remember them as individuals, but if you look at them as a whole picture and that they're all related, then it's a lot easier to remember. If you combine this with patterns, this will help you remember that the cosine of a sum is the cosine, cosine, sine, sine, and the sine of the sum is cosine, sine, sine, cosine. It's easier to remember the whole song, all the lyrics to the whole song, than it is to remember what's the 5th line of your favorite song. Come up with the 5th line of your favorite song without just starting at the 1st and counting up to the 5th. It's easier to remember the whole song than it is to remember each individual piece of the song. When someone comes along and says, what is the double angle identity for integrating cosine squared, or even powers of cosine? You could just like come up with this, and then wait, is it a plus or a minus? You don't have to remember if it's a plus or a minus if you remember where things come from. Sing the whole song. Remember where it starts from. All Like if you tell me to sing the third verse of Yakko's World from Animaniacs, cannot do it without starting from the first. So if you're like, oh, what's the third verse of Yakko's World? I'm like, oh shit. United States, Mexico, I have to do the whole thing. I can't just pick one piece out. But by putting it all together, I can remember the pieces. That make sense? You gotta know where shit came from. So this is what we're gonna do. We're gonna integrate the even powers of cosine using this double angle identity. The reason that this is so useful is that integrating cosine squared, you could look how it's done with parts. That's kind of a pain in the ass, but integrating cosine of 2 theta, trivial. Integral cosine of 2 theta is a half sine of 2 theta. This little chain rule, no funky shit going on. If you can move your constant from an exponent, a power of your cosine, to a coefficient of your argument, that makes things so much better. Then of course you're going to have to get your way out of this, but it's still just more double angle identities out. All right, so next time we'll talk about integrating even powers of cosine using a double angle identity. That's going to do it for today. I'll see you all on tomorrow, and we will spend even more excessive amounts of time integrating products of powers of trig functions that are not substitutions. Everybody have a good day, and thanks for playing.